Welcome to This Explainer. Look, if you're a city planner, a project manager, or really anyone making high-stakes decisions about urban development, you are exactly where you need to be. Today, we're exploring a hidden layer of data that acts as the ultimate decision-making tool for our future cities. We are demystifying digital elevation models.
Okay, let's dive right into this with a massive problem. How do you design resilient infrastructure when you can't truly see the ground beneath your feet? Think about it. When we look at a city, we see trees, we see skyscrapers, we see houses, but if you want to build a new road, lay a new sewer pipe, or predict exactly where floodwaters will pool, all of those visible objects are actually in your way. To build safely, you have to be able to look right past them down to the true terrain beneath.
Here is your project manager's boardroom playbook. Today we're covering foundation of future cities, bare earth versus surface models, ensuring engineering accuracy, modeling urban flood risks, managing and sharing GIS data, and finally, visualizing for the public.
Section 1. Foundation of Future Cities, the 3D Blueprint.
So the core concept here is the DEM, or Digital Elevation Model. It's a 3D terrain representation. But honestly, the absolute most important word to remember here is quantitative. This isn't just a pretty picture. It's a mathematical foundation. A reliable DEM is the baseline blueprint that makes mitigating disaster risks, designing resilient infrastructure, and finding perfectly safe land for new housing developments actually possible. Without a DEM, you're essentially just planning in the dark.
Section 2. Bare earth versus surface models, seeing the true city.
Now, this is a technical distinction that you absolutely must understand, because if you mix these up, your budgets and your safety models are going to be completely wrong. Think of it like an X-ray versus a photograph. A digital surface model, or DSM, is the photograph. It shows the elevation of everything on the Earth's surface, the tree canopy, the buildings, the power lines. But a bare earth DEM, that's the X-ray. It mathematically strips away all that vegetation and man-made infrastructure to show you only the true bare ground beneath. For real terrain analysis and foundational city planning, that X-ray is exactly what you need.
And this brilliantly illustrates why having both of these models is basically a superpower for city planners. If you take your surface model with all those buildings and mathematically subtract your terrain model, the bare earth, you're left with just the object heights. Suddenly, with simple subtraction, you have a perfect 3D city model with exact building heights and tree canopies. That's incredibly valuable for things like urban forestry or running a line-of-sight analysis for telecommunications.
Moving to Section 3. Ensuring engineering accuracy, collecting the best data.
Look, knowing what a DEM is won't help you at all if your actual data is flawed. When you're sourcing data for urban projects, you generally have two main approaches. First, we have airborne LiDAR. This involves shooting laser pulses from an aircraft to measure the ground. It is the absolute gold standard for high-resolution urban projects because it can actually penetrate through gaps in the tree canopy to map the ground underneath. Then there's satellite stereophotogrammetry, which uses optical images from space. It's fantastic for broad regional coverage, but it cannot penetrate the tree canopy and is far less precise than LiDAR. So why should you shell out for that high-resolution LiDAR data? Well, it's non-negotiable for identifying safe, stable land for new housing developments. It ensures that when you build complex horizontal and vertical infrastructure, everything actually lines up. Plus, it allows for incredibly precise cut-and-fill volume calculations. That means your excavation budgets are mathematically accurate down to the sub-decimeter, potentially saving you from massive cost overruns.
But precision is only half the battle, right? You also need accuracy, and that requires understanding vertical datums. Essentially, a vertical datum like a geoid is a reference point that approximates mean sea level. You have to ensure your dam is tied to orthometric heights, meaning heights measured relative to sea level. If your data isn't anchored to a standard vertical datum, your roads won't connect and your water pipes might literally end up trying to flow uphill. It is the ultimate guarantee of engineering reliability.
Section 4. Modeling urban flood risks, preparing for the worst.
The number 2, just 2 meters. That is the vertical standard deviation difference you might see between a high-quality global radar DEM and a true state-of-the-art model. Now, 2 meters might not sound like a whole lot when you're out hiking, but in urban flood modeling, a 2-meter margin of error is the difference between accurately predicting an inundation zone and mistakenly building a brand new housing neighborhood right in the path of a disaster.
To get that pinpoint accuracy for flood models, we use something incredible: machine learning vegetation correction. You can kind of think of this as digital deforestation. Older filters used to really struggle to separate dense forests from the ground. Today, neural networks easily identify and remove tree and building biases from satellite data. This powers advanced datasets like FabDem,
providing vastly superior bare earth results that keep your flood models incredibly reliable, even in heavily vegetated lowland areas.
Let's see how this all builds into a complete hydrological conditioning workflow, because raw data isn't ready for a flood simulation right out of the box. You have to condition it. Take pit filling, for example. It's absolutely vital. Often, digital models have artificial sinks or depressions just due to data noise. If you don't fill the pits digitally, your computer model will think water gets trapped there permanently, which completely ruins your simulation. By filling pits and burning in known stream networks, you ensure water flows exactly the way it should across your digital terrain.
Section 5. Managing and sharing GIS data, the project manager's matrix.
Okay, let's shift gears from data science to cross-departmental project management. As a decision maker, you're going to encounter two fundamental data structures. On one side, we have raster data, which is built on a grid. Think of it like a digital photograph made of pixels, where every single square has an elevation value. It is incredibly computationally efficient. On the other side, we have vector data, like a triangulated irregular network, or TIN. This is point-based and adaptable, using triangles to map complex terrain with high precision, but it's computationally much heavier.
To make your life easier, think of these formats as your cross-departmental cheat sheet. When do you use what? Well, if you're managing raw, unprocessed LiDAR point clouds straight from the engineering or surveying team, you're going to be dealing with LAS or LAZ vector files. But if you want to share an interpolated elevation map with the zoning board, the environmental team, or the mayor's office, you want a GeoTEF. It's a grid-based raster format that serves as the universal standard for sharing GIS data easily across teams.
Section 6. Visualizing for the public. Winning the town hall. All right, you've got the data, you've done the science, but now you need to win the town hall. Let's be real. Handing a city council member a spreadsheet of LiDAR point clouds is not going to get your infrastructure project funded. You need hillshade maps. A hillshade map simulates how the sun would illuminate the terrain from a specific angle, casting shadows that instantly reveal the subtle morphology of the land in 3D. It is literally the ultimate hack for clear, persuasive presentations. It translates highly complex elevation data into an intuitive, visual format that absolutely anyone can immediately understand and engage with.
And that brings us to our final thought. Are your city's future developments built on a truly solid foundation of data, or just an illusion of the surface? By moving past digital surface models and embracing high-resolution, accurately conditioned bare earth DEMs, you are empowering your city to build smarter, safer, and much more resilient infrastructure. Thank you so much for joining me in this explainer, and I really hope this playbook helps you make your next big urban planning decision with total confidence.